This is the video for section 4.5 in AP Calculus on linearization and Newton's method. So we're going to begin by discussing what differentials are. We've been working with them the whole time we've been doing derivatives. So if you have a function that's differentiable, then you basically have two differentials going on there. You have the differential dx, which is when you take derivatives of the independent variable, and it represents the change in x. And then you have the differential dy, which is written as dy, but it typically comes from taking the derivative of x with respect to x. Dy is then dependent on dx because y is dependent on x. And in fact, dy depends not just on dx, but it also depends on x if you still have x values in the derivative once you take it. So let me show you exactly what I mean. It says to find the differential dy and to evaluate dy for the given value of x and dx. This is really not any different than what you've been doing. You're just going to think about it a little bit differently notation-wise. So, for example, the derivative of y, we can write it as dy dx. The derivative of the x to the fifth plus 2x is then going to be 5x to the fourth plus 2. Now, they're wanting us to find the value of dy. If you look at the equation the way that it's written, I don't have just dy. I have dy dx. So if you don't think about this so much as a calculus problem at this point, but as an algebra problem, we can make it look like dy equals if we take the dx and we multiply it to the other side, which is exactly what we're going to do right there. So at that point, then, it becomes a matter of substitution. X can be replaced with a value of 1, and dx can be replaced with a value of 0.01. So dx would be equal to 5 times 1 to the fourth plus 2 times 0.01. And then you just do those calculations. So 5 plus 2 is going to give you 7 times 0.01. And you're going to get a final answer of 0.07. So what that 0.07 represents, it means that with the function y equals x to the fifth plus 2x, when x has a value of 1 and is changing at the rate of 0.01, then the y value would be changing at a rate of 0.07. That's how that exactly works out. And this is going to lead us into stuff further down the road that we're going to get into in the upcoming sections. But it can also be used not just for x and y situations. So this is defined as the differential estimate of change. I'll let you read that definition for yourself, but it's essentially what we just did right there, where you were having to take the derivative but then separate the dy and the dx. But it's not necessarily just x and y that we can do it for. We can do it here, for example. It says the radius of a circle increases from a equals 5 meters to 5.1 meters. Use dA to estimate the increase in the circle's area, A. So they've given us information about the radius of the circle, but then they're asking us questions about the area of the circle. So I need to find a way to relate those two things. So hopefully you remember from geometry or even from elementary school that the area of a circle is found with pi r squared. So then if they start talking about the rate of change of these things, this derivative of a would be dA dr, because the radius is your independent variable, whereas the area is your dependent variable. And then on the right-hand side, when we take that derivative, pi is just a constant, so it's like our coefficient. So when we bring the power in front, that's just going to be 2 pi r to the first. So then if we solve for dA, dA is equal to 2 pi r dr. Now if we're trying to actually find dA to estimate the increase in the circle's area, then that means that in my equation that I have now, dA is my unknown, so I need actual values for r and for dr. So r is going to be the initial value of your radius. The radius of the circle increases from 5 meters to 5.1 meters. So that means the initial radius was 5 meters. The change in r, or dr, if we do end minus beginning, is 0.1 meters. So that's my dr, which would mean that dA is 2 times pi times 5 times 0.1. So 10 times 0.1 is going to give me 1 pi. And then you got to talk about your units. Well, your units, we're talking about the change of the area, then that would be square meters, because area is always a square measurement. So that is differentials and rates of change. How does that then lead us into linearization? So this also goes along with what we've been doing ever since, really before we even defined it as a derivative, just ever since we've been doing this whole concept of instantaneous rate of change and how that connects to the tangent line. And if a function is differentiable, then the crazy roller coaster ride function, if we focus in just on where the tangent line is, the function actually looks like the tangent line. They are one and the same for the most part. So how that leads us into linearization is that since the tangent line and the function are one and the same, when I'm really, really close to that x value where the tangent line is located, that means that I can actually use the tangent line to approximate values of the function if I, for whatever reason, am not able to actually evaluate the function. So that's what this is kind of saying here in this paragraph. You can read through it for yourself, but essentially this formula is your linearization formula. Now, if I take that and make this y, y1, m, x, x1, that makes that equation y equals y sub 1 plus m times x minus x sub 1. Or y minus y sub 1 equals m times x minus x sub 1. This is the formula we've been using. That's point slope form that we've been using to write equations of tangent lines for months now. So this L of x form is the exact same thing as coming up with the equation of the tangent line to do these linearizations. So that's how we're going to do it. So for example, we want to find the linearization of f of x is equal to cosine of x at x equals pi over 2 and use it to approximate cosine of 1.75. We don't know what the cosine of 1.75 is on the unit circle because 1.75 is not one of our special places on the unit circle. So what we do is we find the place on the unit circle that's the closest to 1.75 and use the linearization there to approximate it, since we can't do cosine of 1.75 without a calculator. Pi over 2 is the closest place on the unit circle to having a value of 1.75. If you divide pi over 2 in your calculator, you're going to get 1.57 and so on. So that's the closest to 1.75. So that's why they're suggesting that we use x equals pi over 2. So here's the process that you're going to go through. Your x value is pi over 2. To write an equation of a tangent line, we need a full slope, or a full point, and a slope. So to get the point, I need the y-coordinate of it. So that means I need to evaluate my function for my value of x. So that would be cosine of pi over 2, which is 0. So that becomes my y-coordinate. My slope is going to be to evaluate the derivative at that x value. So the derivative of cosine is negative sine x. So my slope would be negative sine of pi over 2. Sine of pi over 2 is 1, so my slope is negative 1. We've been doing this for months. And so at this point, my tangent line would be y minus y1 equals m times x minus x1. That tangent line can be used to approximate my cosine function for x values that are close to pi over 2, like 1.75. So this translates to y equals negative 1 times x minus pi over 2. You do want to write it in y equals form with the y all by itself before you use it for the approximation, because then we can write cosine of 1.75 is approximately, and then we just substitute our new x, our 1.75, into that tangent line. So it would be approximately negative 1 times 1.75 minus pi over 2. Now at this point, you're not going to have a calculator. Otherwise, it would defeat the purpose of this problem. If you had a calculator, you could have told me what cosine of 1.75 was 5 minutes ago, and we could have skipped this problem. But you're not going to have a calculator. So really, that's the best you can do. -1 times 1.75 minus pi over 2. Now, they may like turn them all into fractions and get common denominators and that sort of thing, which would be -1 times 7/4 minus, so if we want common denominators, that would be 2 pi over 4. And then if we distribute the negative, that would be 2 pi over 4 minus 7/4, or 2 pi minus 7 all over 4. That's the most accurate estimate you could give for what cosine of 1.75 is equal to. Now, if you don't believe me, pull out your calculator and try it. Type 2 pi minus 7 over 4 in your calculator and type cosine of 1.75 in your calculator, and notice how similar they are. So here's another example of how you would do one without a calculator. Square root of 146. If I asked you right now to tell me what the square root of 146 was, you would not be able to tell me exactly what it is. But you could say it's a little bit more than 12, because the square root of 144 is 12. Okay, so you would at least kind of be able to ballpark it and narrow your choices down. But I want to find as accurate as I possibly can an answer. So they didn't say 4f of x equals like they did in the last problem. So the first thing I need to do is I need to figure out what my function is. Well, my function is the operation that I'm doing. In this case, it's square rooting. So my function would be square root of x. That helps me to identify that the x I'm trying to evaluate is 146, but I can't evaluate it without a calculator. So for the x I'm going to use for my tangent line, it needs to be the closest number that I can square root to 146. So that would be 144. So 144 is your x, and then so we need a y-coordinate and we need a slope, because we're going to write our tangent line equation. So to get our y-coordinate, we would simply evaluate the function for 144. So the square root of 144 gives us 12. So the y-coordinate is 12. For my slope, I need to evaluate the derivative. So it might help to rewrite the square root of x as x to the 1/2. The derivative then, if we use the power rule, is 1/2 x to the negative 1/2, or 1 over 2x to the 1/2, or 1 over 2 square root of x, which means that my slope is 1 over 2 square root of 144, 1 over 2 times 12, 1 over 24. So there's my slope, 1 over 24, which means that my tangent line is y minus 12 equals 1 over 24 times x minus 144, or y equals 1 over 24 times x minus 144 plus 12. So if I want to approximate the square root of 146 now, it would be approximately 1 over 24 times 146 minus 144 plus 12. So that equals 1 over 24 times 2 plus 12. So 1/12 plus 12, or 12 and 1/12. And you can leave it as a mixed fraction like that if you want, or it would be 145. That should be a 12, not a 2. 145 over 12. All right, so there's 2 more problems on your notes for you to try. I want you to give the cube root of 146 and the cosine of 3 a try on your own. Pause this video, give them both a try, and then when you hit play on the video again, it will have the work and the answers for those up there for you, but I'm not going to go through the explanation in the video. All right, so you may want to pause it right now so that you can see all the work and the final answer for the cube root of 146, which is down here. And then for the cosine of 3, there's your final answer.